So I'm going to get started. We'll just go through a few examples, and if you have any specific questions, that I can also answer them. Okay. All right. Problem 25.6 from the textbook. Solve the following problem numerically. Dy by dt equal to minus 2y plus t squared with the from t equal to 0 to 3, and the initial condition is y of 0 equal to 1. This is our basic the equation we need to solve. So you can write this as dy by dt equal to a function of t and y, that being 2y minus 2y plus t squared. Okay. So if I go back and look at my first two slides from previous time, I can easily look up or copy this and save a little bit time. Maybe I'll just write it again. It's simpler to do. You can hear me, right, April? Can you hear me?
Yeah, I can hear you.
Okay, good. All right. So the RK4 method, which is the kind of the longest method to use, is y at the next time step equal to y at the current time step plus 1 over 6 multiplied by h, or h over 6 multiplied by I'm sorry, I'll write it as h multiplied by summation aj kj, where j equals 1 to 4 and a1 equal to a4 equal to 1 over 6, a2 equal to a3 equal to 2 over 6, and the values k1 is the function evaluated at t and y, k2 is the function evaluated at t plus delta t divided by 2, and y plus k1 delta t divided by 2, and k3 is the function evaluated at t plus delta t over 2, and y plus k2 delta t over 2, and k4 is the function evaluated at t plus delta t and y plus k3 times delta t. So this is the formula which you need to know, and in the exam either you will be allowed to bring a sheet of notes, or you will be provided this formula. One way or the other, you don't have to memorize this, but you should know how to use this formula, which is what we are going to demonstrate today. And along the way, if there are questions, feel free to stop me and ask. Okay, since it's only one student today, so I have some time to answer questions, more time. All right, so my function, just to recall, function of t comma y is minus 2y plus t squared. Okay, so we are told that y at time 0 equal to 1, and a delta t we are going to use as suggested in the problem is 0.5 suggested. For hand calculations, we'll just use such a very coarse time step. We can of course use a very fine time step for implementing it on Excel or MATLAB or whatever. All right, so first we want to compute y at 0.5 is y at 0 plus, you can write h multiplied by aj kj. H being h is, I'm sorry, I think in the previous slide I wrote delta t. I think I should just use the nomenclature h because that's what I've been using. Sorry, I've been using delta t, so I'll just put it here. So over here I will have y at t equals 0.5 equals y at t equals 0 plus delta t multiplied by aj kj, j equals 1 to 4. This is where we start. This value is 1 as given, and this is what we are trying to calculate. And this value of course is 0.5. So I think Richard just joined. Thank you, Richard. Can you hear me?
Yes, I can hear you.
Okay, so we are trying to solve, or we are doing an example from the book. Problem number 25.6. This is the problem. I'll give you a second to write this down, and then we can continue. So we're going to solve this using RK4 method. Can we proceed?
Yeah, I have it down.
Okay, so we started with writing down the RK4 method. Okay, this is just the formula which you need to know. Either you can bring a sheet of notes, or this will be provided to you. But what we are going to see today is how to use the formula, or how to do the calculation. So we have y at t plus delta t equals y of t plus delta t multiplied by summation aj kj. These are the a values which we already saw. And k1, k2, k3, k4 are 4 executions of the function, which at t comma y, t plus delta t, and then different values of y. And then the function itself, if you recall, that is the right side of the equation. So whatever is your dy by dt equal to, that right hand side is the function, and we'll evaluate it 4 times in order to get the value of the value of the function y at t plus delta t. That's the basic concept. So we start here. The initial condition is y of 0 equal to 1, which is given. A delta t of 0.5 is suggested in the problem. So we'll put these numbers, and now we need to compute the kj values. That is really the goal, or the important thing in each step. Okay. So t equal to 0, okay, and y of 0 equal to 1, and delta t equal to 0.5. These are the numbers to keep in mind. So k1, which is the function evaluated at t comma y, is the function evaluated at 0 comma 1, and you have to take minus 2y plus t squared and evaluate this at t equal to 0 and y equal to 1, which will be minus 2. Okay, so k2 has to be the function evaluated at t plus delta t divided by 2, and y plus k1 delta t divided by 2. Now, what is t plus delta t over 2? That is 0 plus 0.5 divided by 2, or 0.25. I am intentionally doing each step so that this is probably good practice for you to prepare for the exam. If you have questions, feel free to stop me and ask. Okay. And so we have evaluated this. Now we need to evaluate this term, or this value, which is y plus k1 delta t divided by 2. The y value being 1, and k1 is minus 2, which we just calculated, multiplied by 0.5 divided by 2. So this is 1 minus 0.5, or this is 0.5. So k2 is the function evaluated at t equal to 0.25 and y equal to 0.5. So which is minus 2 times 0.5 plus t squared, which is 0.25 squared. So what is this? This is minus 1 plus 0.12, no, 0.625, 0.625, which is, how much is this? 375, right? Minus 0.375. Yeah, minus 0.375. Are you, both of you are with me so far?
Yes.
Okay. All right. So that is K2. All right. So now you need to recall what is K3. K3 is the function evaluated at t plus delta t over 2 and y plus K2 delta t divided by 2. T plus delta t over 2 is easy, that is 0.25, doesn't change. Y plus K2 times delta t over 2 is nothing but, what is y? Y is 1 and K2 is minus 0.375. Delta t is 0.5 divided by 2. So we need to calculate this. You can punch it in your calculator and tell me. 0.375 times 0.5 divided by 2. 0.90625 or minus 0.9063. Am I correct?
I got the same value.
Same value. Okay. So now you need to punch it in K3, which is the function evaluated at 0.25 and minus 0.9063. So that is equal to K3 equal to minus 2 times y. What is y value? Minus 0.9063 plus t squared, which is 0.25 squared. Wait, did I get? Yeah, that's what. 1 minus. Yeah. No. No, I think this is plus 0.906.
Yeah, I see that. I got the. Yeah, it's
Should
supposed
be
to be. It should be positive.
positive. Yeah. So positive. We go here. All right. So this should be minus. Oops. So just yeah, I'm going to just open my Excel and calculate this. Equal to minus 2 multiplied by 0.9063 plus 0.25 squared. That is minus 1.7501. Minus 1.7501. So that is K3. And K4, if you recall, that is the function evaluated at t plus delta t and y plus K3 times delta t. So this is nothing but 0.5. 0 means 0 plus 0.5 equal to 0.5. And this is y plus K3 delta t is 1 plus minus 1.7501 multiplied by 0.5, which is 1 minus 1.7501 times 0.5, 0.1250. Point 1250. So K4 is the function evaluated at 0.5 and 0.1250 is minus 2 times 1250 plus 0.5 squared. What is that? This is minus 0.25 plus 0.6, no, plus 0.25. So this is approximately 0. So just to write it in one place, K1 equals minus 2, K2 equals minus 0.375, K3 equal to minus 1.7501 and K4 equal to 0. All right. Is it okay so far?
Yeah.
April?
I have a question. So the
Yeah.
problem stays to do RK3, and so that's what I did. I did the RK3 method.
That's fine. I'm
And
just trying
so
to use it to illustrate RK4.
yeah. But so in both the RK3 and RK4 method, the K2 formula, I believe, is the same. But I
Okay.
have a different value for K2.
K2. Let's check K2. So K2 has to be evaluated at t plus delta t divided by 2, that is 0.25, and y plus k1 times delta t divided by 2. What did I do here? 1 plus k1 multiplied by delta t divided by 2. So I am getting 0.5. So I need to put minus 2 times 0.5 plus 0.25 squared. Let me just make sure I didn't mess it up. Minus 1 plus 0.25 squared. Oh, okay. I goofed up here. So that is minus. Can you tell me what you have?
I have a minus 0.9375.
Correct. Minus 0.9375. So K3 value gets hit because I used the wrong value. So I need to go back and write minus 0.9375. So if I fix that, that would be 1 minus 0.9375 times 0.5 divided by 2, which is 0.7656. 0.7656. So I have to evaluate the function at 0.7656. Okay, so it's just thing about this whiteboard is I'm able to make corrections. Oops. Give me 1 second.
Okay.
Come on. Oops. All right. So minus 0.9375, we were there. And then we need to fix this minus 0.9375 multiplied by 0.5 divided by 2, which if I do that, I'm getting 0.7656. So this has to be changed. This has to be changed to 0.7656. So the function has to be evaluated at 0.25 and 0.7656. So K3, oops, K3 has to be evaluated at minus 2 times 0.7656. How much is that? Minus 2 times 0.7656 plus 0.25 squared. Minus 1.4687. 4687. So that is K3, and this value here has to be updated 4687. So that's 1 minus 1.4687 times 0.5, which is 0.2657. 0.2657. So that's y plus K3 times delta t. So I come back here, I have to evaluate this at 0.5 and 0.2657. 0.2657, and what will that be? Minus 2 times 0.2657 plus 0.5 squared minus 0.2814. 0.2814. So K1 value is minus 2, no change there. K2 value is minus 0.9375. 9375, and K3 value is what is K3 value? Minus 1.4687, and K4 value is minus 0.2814. Okay. We have this. Next step is for us to write y at 0.5 is 1 plus 0.5 multiplied by 1 over 6 multiplied by K1, which is minus 2, plus 2 over 6 multiplied by K2, which is minus 0.9375, plus 2 over 6 times K3, which is minus 1.4687, plus 1 over 6 K4, which is minus 0.2814. Point 4089. So that is, if I do all these calculations, I get 0.4089. Now I want both of you also to confirm this for me.
Yeah, I got 0.0 or 0.403.
4089. Okay. So this is if you start writing it out as like a table to fill out. So you have time and then the y value. So at 0, 1, this is given the initial condition. At 0.5, we have 0.4089, and then the problem asks you to go up to 3 seconds, or up to 3.0, which of course it takes more steps. But in the exams, I usually will not ask more than like 1 or 2 or at most 3. Okay, I won't ask like to do 5 or 6, which is a lot of work. We'll try to restrict to 2 or 3 maximum. So that is an example where we solved a simple ODE, and we just had a function on the right side which depended on both the variables, both the independent variable time and the dependent variable y. Okay, we had one example. If you look at problem 25.7, we have a system of two ODEs, which we will now try to solve as another example. So problem 25.7, dy by dt equal to minus 2y plus 5e power minus t, and dz over dt is minus yz squared, okay, over 2. Solve this over the range of t equals 0 to 0.4 with a step size of 0.1. So we are asked to solve this from t equal to 0 to 0.4 with a delta t of 0.1. And initial conditions are y of 0 equal to 1, y of 0 equal to 2, and z at time 0 equal to 4. This is the problem statement. So you'll have to do exactly the same procedure as we did for ODE with only one dependent variable. Here there are two dependent variables. Okay, so let me write that down. There are two dependent variables here. Y and z. So you can write dy by dt equal to f of t, y, and z, and dz over dt equal to g of t, y, and z. Of course, f of t comma y comma z is nothing but minus 2y plus 5e power minus t. Z doesn't appear in f, okay, the function f, and this is equal to minus yz squared over 2. Time doesn't appear in the second function g, but when we advance the solution from a current time step to the next time step, we have to evaluate both the functions simultaneously, and that is what we are going to see now. Okay? So if you again recall the RK4 method, I mean, you don't have, it's not that you have to do this always using RK4 only. Other methods like RK3, RK2, or the first order Euler method, they are even simpler because they involve fewer times that we have to evaluate the function. So we can try this with say RK2 or RK4 to save time, just to show you how the method works. Okay, so if I go to RK, or actually if I just take the Euler method just for illustration, Euler method, which is nothing but y at t plus delta t equals y of t plus delta t multiplied by f of t comma y comma z, and z at t plus delta t is z of t plus delta t multiplied by g of t comma y comma z. Very simple. So the catch here is, if you have time and y of t, z of t, at time 0 the initial conditions are given. So we want to do 0.1, 0.2, 0.3, 0.4. At each time step, you have to calculate both these values in order to advance the solution. That is the main catch here. You can't go down one row, one column, and then come back to Z. It doesn't work that way. They have to be done together. So you have to do this calculation together before moving to the next time step. Okay, so we are going to try that. So to get y at t equals to 0.1, we write y of t equals 0.1 equals y of 0 plus delta t, which is also 0.1, multiplied by f of t comma y comma z, and z at t equals 0.1 is z of 0 plus delta t multiplied by g of t comma y comma z. So you need to evaluate f of t at 0 and y at y of 0 and z at z of 0, which is nothing but f of t equal to 0. What is y of 0? Y of 0 is given to be 2. Z of 0 is given to be 4. So this is, where is that function? Minus 2 times y, which is 2, plus 4 times or plus 5 times e power minus 0. So that's just 5. So minus 4 plus 5, this is 1. So f of t comma y comma z, this value is 1. Okay. So then we also have to calculate. So remember that z also needs to be updated simultaneously along with y. So z of t plus delta t equals z of t, sorry, z at t equals 0.1 is z at time 0 plus delta t, which is 0.1, multiplied by g of t comma y comma z. So that is g at 0, y of 0 is 2, and z of 0 is 4, which is, what is our function? That is minus 2 times 4 squared divided by 2. That is minus 16. Okay. So then what is our z value here? Z at 0.1 is going to be z of 0, which is 4, plus 0.5, which, I'm sorry, 0.1, which is delta t, multiplied by minus 16. So that is 4 minus 1.6, which is 2.4. So if we go back to our table in slide 37, y of t or y of 0.1 is 1. No, not 1. Sorry. Oh, we haven't done y of 0.1. Y of 0.1 is 2 plus 0.1 multiplied by 1, which is 2.1. So if you go to this slide 37, y value is 2.1 and z value is 2.4 using Euler's method. Okay. Now using this value that you just computed, let's compute this next time step, which is 0.2, next time point. Why don't we, three of us, do it separately, and then you can look up and we can compare our answers using Euler's method. Okay. So I'm going to be quiet for some time. Why? Sorry. So when you're ready, let me know if you are getting these values.
I got Z.
got-
I'm a little off on Y, but
I got Y. I'm still working on Z right now.
So Richard, what value of y did you get?
I got 2.1324.
Okay, and April, what value of z did you get?
Z, I got to 4 decimal places, I got 1.7952
1.7952. Okay.
for Z, yeah.
And for y value?
My Y value, I got 2.2326.
Okay. All right, so let me check my calculation. So for the y value starting, that is 2.1 and 2.4. That we also got the same, right?
Yes.
And when you do the f of the function value, function f value, that is 0.3242. Correct?
Let me check. Hold up. 1 second. See, I'm getting a 1.3.
Okay, so minus 2 multiplied by 2.1 plus 5 times exponent of minus 0.1. That is the function.
Right. Oh, it's a negative. Okay, that's why I'm messing up. Okay, yeah,
All right.
I got it. Yeah.
So let's just wait for Richard to finish up, and then
I got it.
Okay. So you can fill out this table in this process. You can do Euler's method, which I chose now just to save time. You can do the other methods as well, and the comparison is as the order of the method increases, the accuracy increases with the same time step. But the main thing for the exam is to be able to do these calculations without making any mistakes in the middle, which comes with practice. Okay, so those are 2 examples. I want to do one more example in the 15 minutes we do have, which involves something like a second order equation, so that we can illustrate that as well here. Problem 25.3. Problem 25.3. We are going to write d squared y over dt squared minus 0.5 t plus y equal to 0. So this is a second order ODE with y of 0 equal to 2 and y dashed of 0 equal to 0. Okay, and the book has a typo there. I think they want us to solve from t equal to 0 to 4 using a step length of 0.1. We are not going to, of course, do 40 manual calculations here or in the exam, but I want you to just see how we reduce this second order ODE into 2 first order ODEs. That's the main point here. Okay, so step 1 is to make a substitution. That dy over dt equal to z. So if you make that substitution, immediately the given equation becomes d squared y over dt squared is nothing but dz over dt. So you can write this equation as dz over dt equal to 0.5 t minus y. So we can call this function of t, y, and z, and we can call this a function of function g of time, y, and z. So now you have something in the first line, which is a very simple function. It depends only on z. That is okay. But as far as the solution procedure is concerned, nothing changes from the second example to the third example. That is, this is now a system of 2 ODEs for dependent variables y and t, for y and z, with initial conditions y of 0 equal to 2 and y dash of 0, which is nothing but z of 0 equal to 0. Do you both of you see the common, that is, from now on, this problem and the previous problem are really the same procedure?
Yeah.
Okay. All right. So we can go through this, but I think you will be able to do this on your own. I just want to discuss different types of examples, maybe in the 10 minutes I have. So before I do that, any specific questions at this point?
I don't have any.
Okay. So let's just look at different problems and just try to, so let me share my screen here for a second. So if you see problem 25.19, I think this was one of the homework problems. Okay. The main idea is you are given a first order differential equation in velocity. If your only goal is to solve for velocity as a function of time, this is just one problem. There is just one equation to solve. If your goal is to track both the velocity, instantaneous velocity, and the instantaneous height of this parachutist, then you have to add one more equation to this using the idea that velocity is nothing but the derivative of position. Okay. So if I go back to problem 25.19, we are written dv over dt is g, the acceleration due to gravity, minus the drag force divided by mass to turn that into an acceleration. So to get v of t, we can treat this as a first order ODE for velocity or speed. To get the instantaneous position z of t, use dz over dt equal to v. So then it becomes a system of coupled equations, dz over dt equal to v. So you can call this function of t, z, and v.
We
And
can't
this
see
is
your
a,
whiteboard.
oh, sorry. All right. So this is the problem. That is, this is the equation that was given to you. To get only speed, we can just solve this for velocity and as a function of time. To get both position or height and velocity, we have to make use of the fact of the definition of what is velocity or what is speed, which is the derivative of position. So if we add this to the original equation, we get a system of two equations. You can call the first equation as dz over dt equals a function f, which depends on time, z, and velocity, but of course it depends only on velocity. And then the second equation is dv over dt equal to a function g, which depends on time, z, and velocity. But curiously, it depends only on velocity here. G is a constant, or maybe I should use a different function here. I'll call it h. So h is a function which depends only on velocity again. Depends only on velocity again. Okay, but the rest of the solution procedure is the same. You have to simultaneously solve both z and v at each time step and keep continuing. Okay, so let me find one more example to quickly set up, and then later you can try. So if you go to the textbook, especially the let me see here. Chapter 28, that is basically case studies of ordinary differential equations. So I'll write it here. C, problems in chapter 28. These are all case studies. Okay. So if you go there, let me pick out one problem quickly. I mean, once you've learned system of equations and second order equations, practically this everything reduces to the same template. Okay, either it becomes higher in order, like a third order differential equation, or three simultaneous variables, something like that. So there is no more different concepts for you to learn, except you have to do the calculation very carefully. Just trying to find if there is any third order differential equation in this. Actually, no. Throughout that chapter 28, there are only second order differential equations. Yeah, I'm not finding any new variety other than, to summarize. So we have first order ODE of the form dy by dt equal to a function of t and y. We have a second order ODE, which is d squared y over dt squared, which could be a function of t, y, and dy by dt, which you will then reduce, or which you will then use the substitution dz over, I'm sorry, dy over dt equal to z. So you get two equations, d squared y over dt squared equal to function of t, y, and dy by dt splits into two equations, dy by dt equal to z, and dz over dt is a function of t, y, and z. So that is the second type we saw. Okay. And the third type is two simultaneous ODEs for y and z versus time. So you have dy by dt equal to a function of t, y, and z, and dz over dt a function of t, y, and z. So you will have an initial condition for each. This usually is given. That is, initial condition is of course part of the problem specification. Okay. Any questions?
If the initial conditions aren't given, are we supposed to assume for, like, say we have like a rocket launching
Sure.
and we assume the like the y is equal to 0?
Yeah, I mean, usually if you choose the coordinate system and you choose the ground to be your origin, so that means its starting position is y equal to 0. So in that case, it might be left unsaid, but you have to logically assume it.
Okay.
But if the rocket is launched with a certain initial speed, that is something it has to be given. If it's
Okay.
not given, then the problem cannot be solved.
Okay.
So yeah, that's a good question. That is, if this represents a rocket launch problem, this probably is something you can judge, but this has to be given.
Okay.
Yeah. And most likely for the exam, I will provide the all the numerical methods that you need to use, like as a printout, and everyone will have the same set of information. It's like me providing you the cheat sheet. Okay. So tomorrow in class, we'll be continuing and wrapping up statistics. But on Friday morning, I will do a few more examples on differential equations. And then on Monday, I plan one more a session like this, where we'll do some examples on statistics, and Tuesday is the exam. Okay. Stop my recording here.